All right, guys, we're back from our break, and it looks like right now no one else has popped back on after that break. I realize you guys have things that pop up and they have limited time, so that's okay. I'm just going to go ahead and talk about the things to wrap up this section, and then I'll post this video and you can watch it at your leisure. So what I'm going to do is just go ahead and share my screen again. I think I've got the iPad stylus working. We'll see. But there we go. It's taking a little bit of time here. There we go. So what I want to do is kind of walk through one more conversion and kind of one more setup for the de Moivre's theorem, just to help you through those problems, and then show you our Desmos activity, which you only have one in this section, and then your WebAssign to work on for 6-6. So I want to set up this problem as what it would be, and then we're going to break it down into our different steps. So the problem asks you to take a look at simplifying -1 plus I squared of 3 all raised to the 10th power. Now, when we look at this problem, this is actually several problems built into one, kind of like the last one was. If you look back at your notes, we had one that was similar to -1 plus I squared of 3 in converting to standard form, but not exactly. So in this particular case, our first step is to convert -1 plus I squared of 3 to trig form. You've got to do that first, and then go back in and use de Moivre's theorem. So that's kind of long, and let's just focus on step number 1, and then we'll start a new subproblem for that too. So when we're looking at this, first thing we want to do is try to visualize what this complex number looks like in our complex plane. So remember, we'll do our real axis, our imaginary axis, -1 on our real, and then square root of 3, we're going up square root of 3 on our imaginary axis. So close to 1.7, so something like this. So we can draw in our radius. And if we think about a triangle that we're forming, I would probably go ahead and just draw straight down. Now, one of the downsides to this is when we think about our particular angle, we've got a bit of a problem. Not a big problem, but when we think about -1 plus I squared of 3, the angle that we're thinking about is the rotation angle starting from the x-axis to get us where we want. But when we draw this picture and drop our line straight down to our x-axis, what we actually have is a reference angle. So in this case, sometimes it's helpful to, again, use that reference angle notation, because if we can focus on that particular angle, then we can figure out what our original angle theta would be. So let's go ahead and just draw that angle, draw a little bit larger here. We're doing a right triangle, so can put that symbol in. We've got theta prime, the reference angle, and then I've got, if I'm just ignoring the positive and negatives, then this guy is 1, and then this guy is square root of 3. So in this case, the tangent of our reference angle is square root of 3 over 1, or just square root of 3. So if you look at your unit circle, we're trying to find the angle whose tangent is square root of 3. Now, you could also ask Desmos to find the arctan, or ask yourself, what is the arctan of square root of 3? And make sure we can get that particular angle. So looking at your unit circle or using the arctan, what we're actually going to find is that this tells us our reference angle, in this case, is pi over 3. So what we're able to do in this case is think back to our picture. If our reference angle is pi over 3, then we have to go pi over 3 back up to get to this guy. So think about if we rotate it all the way down, all the way down like this, that's pi. This guy is pi over 3. And so our angle We should put that in a different color. The angle that we're looking at here is 2 pi over 3. Now, the other thing that we haven't done is find the radius. Sometimes I do that first. In this case, I was thinking on the angle, not a problem to go back and do it after. We think about looking at our right triangle. The radius is going to be the square root of 1 squared plus the square root of 3 squared. So in this case, we've got 1 plus 3, which gives us 4, and the square root of 4 gives us 2. So in this case, our radius is a little bit cleaner. Now, what are we going to do in terms of putting in the trig form? If you know your radius and you know your angle, you're good to go. So this becomes 2 times the cosine of 2 pi over 3 plus I sine of 2 pi over 3. All right, so then we've done kind of the first step. We've converted this to trig form. And at this point, let's kind of do step number 2. No big deal. Use de Moivre's theorem. And we're going to take our -1 plus I squared root of 3 to the 10th. And what we're doing is replacing it with our 2 times the cosine of 2 pi over 3 plus I sine of 2 pi over 3. Now, these parentheses are a little bit tricky with our nested parentheses, but we're raising all of that to the 10th power. Maybe we should use some brackets. These parentheses a bit. All of that gets raised to the 10th power. And at this point, now we can use de Moivre's theorem. So in this case, let's switch our colors back. And de Moivre's theorem says, raise your radius to the power, the 2 to the 10th, and then cosine of, use that 10 as a multiplier on your angle. So we're going to have 10 times 2 pi over 3. Now, if I'm thinking about it, I'm just going to write 20 pi over 3. And I'm just going to put it in a different color to emphasize that multiplication by 10. And then we want to also do the same thing here. Now, in this case, I don't put the exponent of 10 anymore because I've gone ahead and taken care of that with multiplying the radius, or raising the radius to the 10th power, and then multiplying our 10 by our argument. Now, at this point, we want to stop and maybe simplify what we can. You want to go ahead and do the 2 to the 10th all the way out. You could. I'm just going to leave it as 2 to the 10th for now, simplify at the end. And then if I think about my cosine of 20 pi over 3 piece, this 20 pi over 3 is actually going to go ahead and be able to be simplified first. So if we think about kind of some scratch work, 20 pi over 3 is not between 0 and 2 pi. So, and I think we have one person joining us. So you're welcome. I'll ask for questions in a second. You'll be able to unmute yourself here. But for our 20 pi over 3, you want to think about subtracting multiples of 2 pi. Think about 2 pi is going to be the same thing as 6 pi over 3. So we can subtract multiples of 6 pi over 3, or in this case, 18 pi over 3 would be 3 rotations. So if we subtract this back out, 20 pi over 3 is really equivalent to 2 pi over 3. Then when we take a look at putting this back in, it allows us to condense this back. Now, this particular one is kind of cool in that when we reduced this 20 pi over 3, we got back to a 2 pi over 3, which was actually the angle that we started with. That doesn't always happen. But the 2 pi over 3 here, I can now go ahead and go back to my unit circle and think about what those values are. So cosine of 2 pi over 3, looking at our unit circle, is -1/2. So we're kind of moving it back to that standard form. And then I times the sine of 2 pi over 3, looking at the sine of 2 pi over 3, that's going to be square root of 3 over 2. And then if I think about these 2's, I can go ahead and do a little bit of condensing here. If I do 2 to the 10th divided by 2, that gives me 2 to the 9th. So if I'm distributing these guys, I'm going to have negative 2 to the 9th. And then for this guy, the 2 to the 10th divided by 2 gives me a 2 to the 9th, but I still have a I, and I still have a square root of 3. Now at this point, that looks pretty terrible. What we want to do is go in there and clean that up. You just do 2 to the 9th in Desmos, you get 512. So this is negative 512 plus 512 I square root of 3. So at this point, using de Moivre's theorem allows us to clean this up to put it back in A plus BI form. Not quick and easy, but doable. So I think this is a good point. We'll stop and ask if there's any questions, and then I'll talk about expectations for how to approach this section, how to prepare yourself for the Unit 3 test. We'll talk a little bit about that as well. So any questions? If you have a question, you can unmute yourself and ask. Okay, so no questions so far. Let me talk about that Unit 3 test. So a couple things just in general. I know that everyone has lots of different things going on right now. So my goal is to help every one of you succeed in finishing the course. And things are going to be a little bit different in terms of delivery. Obviously, I've got some things to work out with our delivery and making all the technology work a little bit more seamlessly. But it looks like we are going to be online for the rest of the semester. I'm actually going to go ahead and stop sharing the screen. I think we need that right now. But since we're going to be online for the rest of the semester, we are going to be taking our Unit 3 test online, and I anticipate our Unit 4 test online as well. CVCC hasn't made a formal announcement in terms of, the full plan for the rest of the semester, but that is my current plan. So in terms of Unit 3 test, tell you guys what to expect. So as you're doing your web assignment or preparing, you can go ahead and, optimize your study time. Unit 3 test will be online. I will set it up in WebAssign as a WebAssign test. I will give you access over the course of a couple of days, probably 2, maybe 3 days, and you'll be able to go in there and access it, and you'll have a limited time once you open it. So it'll kind of simulate a timed test, but our requirements are going to be a little bit different. I'm going to allow you guys, since you're taking it at home, we've got this different delivery method, and it's just different, to use a note card. So the other reason for a note card is as you're studying through this material, it's going to help you organize what you know and what you need to clarify. Or at least that's my hope. So you can put things like de Moivre's theorem, examples of this, converting to complex form and trig form and standard form on that note card. Things that we have with vectors, the notation that may be familiar, like a 4x6, a 3x5, really anything you have is fine. Cut a sheet of paper to 4x6, you're good to go. So be building that as you go along. I don't have a test date up there yet. I need to look at my calendar, get those dates up, but we have 2 more sections. So we're not particularly close to our Unit 3 test. So hopefully that will help you, particularly on some of these trickier parts. de Moivre's theorem has a lot of moving components that you can mess up. So let's go ahead, and I'm going to pop this over to Blackboard and show you what else you need to do for the 6.6 work before you start the WebAssign. So the last thing we have, I'm going to share my my WebAssign, or excuse me, my Blackboard page here. So if I share this, it's going to get in there, but I'm going to show you in the Assignments tab. I went ahead and opened up, let me turn off this editing, it'll look a little better. If you go into your Unit 3 explorations, it looks like I didn't open it up. Sorry guys, let me open that up now. Your 6.3 was already open, that was the vectors. 6.6 is now available. So you can go ahead and click in there with me if you'd like. And in 6.6, there's only one Desmos activity that I mentioned, and then you have the digital exploration as well. There's a little bit more in 6.6 that our book covers that I'm not going to cover. I tried to focus on our core components and what we really needed to get out of this section. So as you're reading through the textbook, if it's not converting to complex form in de Moivre's theorem, we can kind of skip over it for right now. Then when you're looking at this Desmos trig form of a complex number, I just want to show you a few things in there. I'm going to switch over to the teacher view and kind of walk you through some of the things that you're going to do in here. And then I'll give you a few minutes to either ask questions or to get started and ask some questions on this. One of the first things we want to do is make sure we can plot complex numbers and interpret where they are in our plane. So those ones, they just have you identify the components like the A and the B, and then kind of where they are over here. Those ones should be pretty straightforward. Then in terms of these ones, you're evaluating like radius length or the modulus. And then starting on, as we go further along, you kind of do a little bit more with the radius not being whole numbers and kind of move these points around and see. And then we get into the angles. The angle here, it's going to challenge you to think about how to use those reference angles and what we did in all of these cases to make our angles work out. Now, it's going to kind of recap a little bit of your trig form for some specific ones. So you want to try to work through finding that angle, finding the radius, and then plugging in. Notice the nice thing about this is it's kind of already set up the form for you so you can plug in the right places. Then this Desmos one only has 8 slides or 7 active slides. The last one is going to be working through a card sort. This one is probably going to be the toughest, and what it's going to put together is thinking about standard form. So for example, if I pull this -7 + 4i card, I need to find the graph that goes with it. So let's see if we can find it. -7 looks like the only one with an x value or a real axis of -7 looks to be here, and then +4i, that seems to work. So, oops, didn't mean to put those two together. Let me clear some of these out. So if I put together these guys in my card sort, then I also want to find the corresponding trig form or the corresponding polar form. So that would require you to kind of sketch this on paper, find your radius, find your angle, and then compare. Okay, so notice all of these ones are in radians and not degrees, but you can kind of think degrees if that helps you, and then convert back, or think entirely in radians. So you'll find the one that matches. This is not necessarily it in this case, and then link it to it. Now, in terms of other things to be careful of, you do have some places where, like for example, this is a trig form of a complex number, and notice you can tell from this that the radius is 2 and the angle is 0, meaning you're not rotating up any. Now, we know that sine of 0 is 0. So if you think about kind of replacing this, this is really 2, or just 2 over and 0 rotation. So you can kind of think about pairing some of these if you can look at it and tell what it should pair with, like maybe those two. But this is going to give you practice with converting between standard form and trig form. What it doesn't give you practice with is the de Moivre's theorem. Again, that's kind of the trickiest part of this section. You have a few on WebAssign. I tried not to overwhelm you with just a sheer number of those. I think I put maybe 3 on there, 3 or 4. And those ones you can work on if you're struggling with getting de Moivre's theorem worked out. We do have kind of a flex day tomorrow that I want to talk about. Your flip day was scheduled for tomorrow,
and the flip day follows a Monday schedule. So what I will do tomorrow during our class time, I'm not planning any new lecture, like this is it, but I'm going to be live during our class to answer questions. So if you have a chance to get in and try this Desmos activity and you're getting stuck, let me know. I can work out some of the things on our card sort or other slides. Or if you're trying your WebAssign and you're getting stuck on the De Moivre's theorem, I'm happy to work a few more examples. You can email me ones ahead of time, or you can pop on here during live parts and take a look at it. So I'm going to stop that share and open up to you guys for questions. So what questions do you guys have, either about due dates or logistics? Remember, you can unmute yourself and ask here. Okay, so what I'm going to do is I'm actually going to stop our recording so that